This exercise will show us how to use ModPaths to develop flow paths from the analysis that we've been conducting. We'll do this in order to understand how water flows through aquifers, the path that it takes, and the bigger picture is that this will allow us to identify flow cells and also give us insights into how we need to set up groundwater models that are at a somewhat larger scale than the ones that we've been setting up so far. So on the left here we have a picture of a simple watershed. This is the topographic divide, and anything falling in here, a marble that falls in here would roll downhill and go past this point. So what we want to be able to do is set up groundwater models that generate what these flow divides are for groundwater. For surface water, it's easy because you can see the topography and you assume that in most cases the divide is the topographic divide. But for groundwater, it's not quite so easy. And to illustrate that, what I'm going to do is to take a look at this groundwater divide, or take a look at this watershed and idealize the pattern of surface water in a model. And so what we'll do is look here. We have a stream reach here that comes up, and we've got reaches that go at a high angle to this main reach off of it. And then we come up here, here we have kind of a branch, but here's another reach that comes at a high angle. And if we look here, we've got a reach, and these reaches come out like so. There would be presumably some kind of a groundwater divide right in here, and another one right in here. So what I'm going to do is idealize this fairly complicated geometry by saying this reach here is the main reach of the stream, and these are tributaries. And this is another main reach and tributaries coming off of it. And so there'll be a divide between these two main reaches right here, and each one of these tributaries will have a capture zone. So if we imagine there's a gauging station right here, there'd be a region something like this that would feed water during base flow conditions to this gauging station. Okay, so soon we'll go and set up models that look like this, that are realistic. But just to get started, it'll be convenient to start with something very simple. Now the extent of the model will be what we see here. So we're assuming that there's a no flow condition right on the other side of, well, actually what we're assuming is this will be constant head, and that by symmetry we'll have the same conditions on this side, on the lower side, as we do on the upper side. Similarly, this will be a symmetry boundary. So our model will look like this square region. And this is the map that we'll import. We've got the heads here, and so this is just set up very much like what we saw in some of the earlier models, where we specify heads at particular locations, and we assume that the heads vary linearly along these stream reaches. Now, what we'll do is assume this is homogeneous, and we'll put some recharge on it, and we'll develop some hydraulic heads and trace the water flowing through it using ModPath. And so this is what the results will look like. If we use a recharge of 1 e to the minus 8 meters per second and hydraulic conductivity of 1 e to the minus 6 meters per second, and the aquifer thickness is 75 meters, then we get a pattern that looks like this. These dots are particles that enter the water table at this location, and then these lines are the path lines as the water flows from this point to the point where it leaves the system, leaves the groundwater system here at this stream. So What we can do is take a look at these particles and the trajectories that they make through the system, and we can see some of them go to this stream, some of them go to this stream, and we can start here at our gauging station and go and mark out the region that where recharge would go to a stream and then pass this gauging station. And if we do that, we can see that it kind of traces up along this route, comes here through these points, maybe around this line right here comes from that point, so it would go between these points, around between these points, and something like that. So if we draw it in, we would have a region that's something like that. This is the capture zone that would this is the capture zone for this particular gauging station, according to our model. Okay, so fairly straightforward, and this gives us a result that's pretty much along the lines of what we were expecting. Now, one of the issues is, though, that will this capture zone stay the same? And what I think we can show fairly easily is that it doesn't. We'll do another analysis where we drop the recharge. This recharge is corresponds to about 1 foot per year, and that's possible. That happens in some places, but we could easily have a lower recharge, and we might imagine that the recharge in many places would be varying through the year. So even though this might be a yearly average, and sometimes the year it would be higher and sometimes it would be lower. So we're not going to look at that temporal variation just yet, but we could imagine that we would have, say, a 10 times lower recharge, and we'll just do a steady state analysis and look at what happens when that occurs. So here is that result. So all I've done is changed the recharge, and we get really a much different pattern to the capture zone. And you can see what I've done is put these points in, trace the flow along from the points to the discharge point, and then gone in and I drew in this line here that marks the capture zone for this particular gauging station. So if we compare them, there's the capture zone for the higher recharge, and then we change the recharge and we get this other kind of asymmetric zone. It's asymmetric because there's a gradient along this stream. So the heads here are higher than here, and these are higher than here, and that gives us this overall asymmetry. But that's typically what we would expect to find, this kind of gradient. So this has several implications related to hydrology. If we have a variable recharge rate, then what we should expect is the capture zone for a particular watershed, ground watershed, the capture zone will vary. The location will move around. And so what it means is if we were to have say we had a contaminated site here that was leaking contaminants into the groundwater, when the recharge was low, we would have flow down here towards this stream. But when the recharge was higher, the flow direction would switch around and would go towards this stream. And so that would cause the direction of flow to move around, and indeed the capture zone to shift. So this is important because it'll cause splitting of plumes, or at very least a smearing out of groundwater plumes. It also gives us some important insights into how we're going to set up groundwater models. We know that there are going to be groundwater divides at the boundaries of flow systems. This would be a no-flow boundary. Well, right now, this white line would be a no-flow boundary. There's no flow that crosses it. And so it might be tempting for us to bound the flow system that we want to simulate with a no-flow boundary. And in fact, that's what we've done for the models up to this point. But what we see here is that we can't anticipate what the boundary is ahead of time, so long as the boundary is just defined hydrodynamically. If the boundary is defined by the limit of the aquifer itself, then we can do it. But if it's just defined hydrodynamically, then it's difficult to do. And so the approach for this, the way you get around it, is that if we're interested in this region right here, the region that drains to this point, then what we do is make a model that's bigger than that, say that goes out 2 or 3 times larger than the region that we're interested in, perhaps even further than that. And we simulate the region all around it so that we don't have to specify what the boundary on the region that we're interested in, where these flow divides occur. We don't have to specify that. We can let the model tell us where that is. And that's an approach that we'll use from now on to set up the models. Okay, so in order to do this, we need to learn a little bit more mechanics of how to set up these flow paths. And here's the comparisons where I've removed the heads and just show you the 2 different capture zones, and you can see that they're quite different. Okay, so we need to be able to run some path lines and generate these path lines using mod path. So here's a quick summary of how we'll do it. So in the Project Explorer, you go to Grid and toggle on this Show Mod Path menu. There should be a menu up at the top of the screen that says Mod Path, and if there isn't, this is where you will turn that on. Then you should put in a new coverage and select this coverage when you add points to the model. You don't want to put the points that you're using for path line tracking in a coverage, say, that you're using for recharge or hydraulic connectivity. Then you select those points, right-click on the selected points, and you'll have a couple of options. You should select the one that says Select Intersecting Objects, and that will allow you to use those points for path lines. And what you may need to do, and if it's not all done already, then go to the Project Explorer, and there'll be something called CCF. This is cell-by-cell flow. Right-click on this, and you'll have cell-by-cell flow to data sets. Click on that. That generates the data sets for flows in the different directions. And that's what the path lines will use that's what ModPath will use to generate the path lines. Then you need to go to ModPath and pull that down, and there's a selection that's called Generate Particles as Selected Cells. So up here we've just selected the objects, and when we click on this, we'll generate path lines from those points. And I'll often toggle between the 3D grid data being off and on. I usually turn it off when I put the particles on there, so you can see the particles, and then you need to toggle it back on so you can see the path lines. Okay, so that's how we'll do it. Let me give you a quick demo. If we go to the to this model, here's the model. This is the base map, and this is set up just the way we've done it in the past. We have the using a conceptual model. We have boundary. We have recharge and hydraulic connectivity, and we can see what those are. We're starting out with a recharge rate of 10 to the minus 8 and a connectivity of 10 to the minus 6, some vertical anisotropy. And the grid, we can go ahead and put in a new grid. I already have one in here, but we can do that again. So the model dimensions are here, and what I'm going to do is make this grid 80 by 72, and I'm just going to have one layer in the grid for now. So hit OK, and that gives us the grid. It also resets the stuff we have over here, so we have to go back and add in a new mod flow and hit OK there. And what we have to do for this is to set up the starting heads, and the default is for them to be at 0, but for this model to work we need to have starting heads that are higher than the model boundary. And the model is set up with elevations that go up to about 250, so we'll set the starting heads above the maximum head in the model at 250. So now we can go ahead and run this, map it to a mod flow. And we run the mod flow model, so we'll save it. And there's the results. We can see we've got some high heads here, and the streams are some lower heads. The way this was set up with the streams was that we made these arcs, and we enter in the points right here that specify what the heads are along these arcs, and we do linear interpolation between them. Okay, so here's the CCF that I told you about, and these data sets are shown right here. So these are the flows in the different directions. The front of the cell, which is along this side of the cell, and the right side, which is along this side. So that'll give us the flows in the different directions. Okay, so I've turned off. So we look up here, and if we want to do mod path, then we need to have an entry here on the menu that says mod path. So what we do is we go to grid, right click, and then show mod path menu. If we do that, then there's mod path. That's what we'll use to run the mod path program. The mod path will be a separate analysis that will be run, and it's set up nicely to run automatically, but we have to enable it here. Okay, so now we need some starting points, and in order to do that we want to go and select this new coverage. So the points we put in are entered into this new coverage, and we might just name this coverage starting points. And let's see, we'll go and put some points in here, and we just put some points around in the vicinity of where we think some good starting values would be. We can add more points later, so we don't need to put all of them in right now. So we put the points in, and the procedure will be to select these points, right click, and then select intersecting objects. And there's only one option here, 3D grid cells. That's what we want them to be, so we hit OK. And now we go up here to mod path, and this entry here, generate particles at selected cells. That's what we want to do, so we select that. And this gives us some options about where we want those particles to be. So for our purposes, right now we want them to be at the water table surface. So we imagine that the water is moving down through the vadose and recharging the aquifer at this point, and then we want to trace the trajectory of that particle through the aquifer. So water table surface is what we want. Hit OK. and then we generate this thing where these are the particle data set that we've just created. We don't see anything though because we've toggled this 3D grid data off. If we turn it back on and go to the heads, then we see the hydraulic heads that we were just looking at, and we see now the flow paths through the aquifer. And we can see now some of these particles go to the stream, and some of them go to other streams. Right? So we're starting to see the capture zone take shape, but we might want to define it in a little more detail. So we could go back and put in some more points. If we wanted to do that, we could go back here, and if you go and put in an additional point right there, one of the difficulties is you don't see it because the heads are being displayed. So I'd like to turn off the display there of the heads, and then we can put in some more particles. So kind of fill it in, and then we just repeat this process where we go and select these heads, right click, or select the points, select intersecting objects, say OK, and now we've got those points selected, and we generate particles at the selected cells, say OK, and go back to our grid data, and there are the particle flow paths for those additional points. Okay, so that's the basic approach for putting in these particles and tracing them. There's a video, and there's also a hard copy or electronic PDF of the instructions about how to use ModPath, so you should review those as well. This will get you going for doing this simulation with just a single layer, and I'll do another video to show you how to do this with multiple layers.